Yes, good morning students. Today we will discuss an examination problem on BMD and SFD. So here, this is a problem given in January 2021 question paper. The question is draw BMD and SFD, locate the point of counterflexion and also find the maximum bending moment. So we have to draw the bending moment diagram. Here for the diagram for this given beam. You can see that this is an overhanging beam. It has this B is called as the overhang. Beyond the support, you have a span of the beam. It carries 2 point loads and 1 UDL. So these are the details of the beam given. So for this beam, we have to compute the bending moment and shear force at important sections or points, and then we have to draw the BMD and SFD, and also from the diagram we have to get the point of counterflexion, and also we have to find the maximum bending moment. So in the earlier classes you have seen that maximum bending moment occurs at the point where shear force is 0. So to find the maximum bending moment, we have to locate the point of maximum bending moment or point of 0 shear, and then only we can find out the maximum bending moment. Now the first step in such types of problems is to find the reactions. So this is a simply supported overhanging beam. So definitely you have only 2 reactions. Supports are at A and B. So reactions I am going to take it as RA and RB. So those reactions are found out using the equilibrium equations. So by taking the algebraic sum of the moments about the one of the supports, we can get one reaction, and by using the second equilibrium equation, that is the sum of algebraic sum of upward forces and downward forces, that is sigma Fy is equal to 0, you can get the other reaction. So this is how we can calculate the reaction. First I have used the moment equation. So I am taking algebraic sum of all the moments taken about the support A as 0, it is one of the end supports. So for that we have to have some sign convention. So normally we take clockwise moments positive and anti-clockwise moments negative. So here, so this if you take the moments of all these forces including reactions about the point A, you can see here this 15 kN is giving a clockwise moment about A, that is 15 into 1, plus this UDL is converted to concentrated load, so 30 into 3, 90. So 90, and it acts at the midpoint. Midpoint is at 1.5 meter from A. So there is also giving clockwise moment. So plus 90 into 1.5. Then this 15 kN is giving is also giving a clockwise moment. 15 into this distance from point A it is 7.5, and that is equal to the anti-clockwise moment, which is given by this RB. So RB into 6 meters about the point A. So this is the equation. If you simplify this, you will get RB as 43.75 kilonewton. Since the value is positive, it is acting upwards. Our azimuth direction is correct. Then using the other equilibrium equation, upward forces are RA and RB. So the sum of upward forces RA plus RB is equal to sum of downward forces. So 15 plus 15 plus 90. So therefore, if you substitute for RB in this equation, you will get RA as 76.25 kilonewton. This is also positive, that means azimuth direction is correct. If the value of reaction comes out to be negative, then the reaction acts in the opposite direction. That's all. Now let us plot the bending moment diagram. For that we need to have the values of bending moments at different salient points on the beam. So here salient points means where the concentrated is acting, where the UDL starts and where the UDL ends. If there is an external moment given, so those points and supports, they are all the salient points. Now I will start taking from the left side of the beam. So I will start from point A. So remember that for calculating bending moment, the sign convention is this. So in the last class, I had explained about this. So suppose if this section is XX, you take any point on the beam, that is XX. If you see the left side of the section, upward forces cause positive bending moment, downward forces cause negative bending moment. Similarly, if you take right side of the section, then also upward forces cause positive bending moment, downward forces cause negative moment. So here upward forces what they cause, we take it as sagging bending moment. Downward forces what moments they cause as sagging bending moment. So this I have explained in the last lecture. So this is the same convention we have to follow. Now at the end support, you know that the bending moment is 0 because nothing is there to the left side of that. Now next point is C, where this 15 kN is acting. See to the left side of C. So this 76.25 is acting upwards at a distance of 1 meter. Since we are calculating momentum, we have to multiply the force by the level arm on the distance. So 76.25 into 1, which is positive because it is acting upwards, and this much UDL is acting from A to C, that is 30 into 1, and it is acting at the midpoint. So it is acting downwards. So 30 into 1 into 0.5. So it becomes 30 into 0.5. If you simplify this, you get 61.25 kilonewton meter. I have written the unit here, that's why I have not written in each step. So 61.25 is the positive bending moment which is acting at C. Then I come to D. So at D, you can choose right side also. So bending moment and shear forces, they are calculated by taking either left side of the section or right side of the section. You get the same value. So if I take right side of this D, only two forces are there. One reaction and this force. So this is upward. So 43.75 into 3, that is positive, minus 15 into 4.5. Distance is 4.5. That is what I have written here. If you simplify that, 63.75 kilonewton meter is the bending moment at D. Now bending moment at B. Next point is B. So at B, if you want to calculate, take see to the right side. Downward force is there. 15 into 1.5. That is 22.5 negative because it is downward force. And at E, if you see the right side of E, nothing is there. Therefore, it is 0. So please observe that at A and E, bending moment is 0. In between, you have some values. Now, let us see how we can plot that. So here you can see that before plotting the bending moment diagram, I have plotted the shear force diagram first. So without calculating the shear force at each salient point, we can draw the shear force diagram. That is the easy method. So let me explain that method. So here, what happens? I am here now. I am at point A now. Draw a horizontal line that represents the axis of the beam. Now positive values are plotted above that line, negative values are plotted below the line. If first I will draw the shear force diagram, I will tell you the easy method of drawing the shear force diagram. So mark the salient points here, A, C, D, B and E. Now for the time being, those are the salient points. Now at A, see only the vertical forces acting on the beam at the salient points. At A, you have a vertical reaction of 76.25, which we have calculated RA. So move upwards by 76.25. This need not be drawn to some scale, just you have to write the values. So I have shown the arrow here. Start from point A. So move upwards by 76.25. Then you have from A to C, you have UDL. How much UDL? 30 into 1. So if you convert that UDL to concentrated load, it is 30 into 1, that is 30 kilonewton. That 30 kilonewton is acting downwards, therefore the profile is linearly decreasing because it is downwards. So I am showing the arrow here. So you have to take this difference as 30. So from A to C, you have a total load of 30 kilonewton. So 76.25 is there. Minus 30 means 46.25 here. Now at C, you have a load of 15 kilonewton downwards. So you have to come down once again 15 kilonewton. So 46.25 minus 15, 31.25. So you have two values of shear force at C. You can see here. So I told you in the last class that at a point where point load acts, you have two values of shear force. Now here we are here now. Now from C to D, you have once again UDL, which is 30 into 2. Total load will be 60 kilonewton. So you have to come down by 60 kilonewton, linearly decreasing. 60 kilonewton you have to come down. Already 31.25 you are there above the line. So therefore 60 minus 31.25, which is 28.75, it is negative now. We are moving down the line now. So therefore this becomes negative. So you have this total will be 60. From here to here, this will be 60. So from here to here, this is 30. So UDL is converted to concentrated load. So this is total 60. So 31.25 minus of minus 28.75 is 60 kilonewton. Now I am here now, D. Now from D to P, there is no force given. There is no reaction, there is no external force. So shear force remains constant. So it's a horizontal line. See here. It remains constant. So at B, 28.75. Now at B, you have a reaction of 43.75. You have to move upwards by 43.75. Already 28.75 below the line is there. Another 15 I have to add here, because this total will be equal to that reaction 43.75 upwards. So therefore this 15 you are going to get here positive. Then from B to E there is no force, there is no reaction, so shear force is constant, so horizontal line. Then at E you have a downward force of 15, so move down by 15, it closes here. So this is very important. Your bending moment diagram and shear force diagram should close. So I have started from point A and I have ended at point E. So then join these, all these are straight lines. In the last class I have told you about the profile of shear force diagram and bending moment diagram. So shear force diagram is a straight line for point load as well as for UDL, whereas it's a parabola for uniformly varying load or triangular load. But here this problem, he has given only UDL and concentrated load, so all the points you have to join by straight line only. So this is the shear force diagram. If you observe the shear force diagram, you can see that at one point F, shear force is 0. At one point F, so shear force is 0. That means the point where the shear force diagram line cuts the axis. So I have taken as F1. So this is the point of 0 shear force. And I told you that at the point of 0 shear force, you can have maximum bending moment. Now let us find the maximum bending moment occurs at the section where shear force is 0, that is at the point F here. Now first we have to locate that point where the shear force is 0. For locating the point, so we have to write the expression for shear force at F. For writing the expression for shear force at F, we have to use once again the sign convention. For shear force, sign convention is like this. If you take any point or section on the beam, XX, if you see left side, this is sign convention. If you right side, this is sign convention. But here we should be careful that you have to take only the forces and reactions. You should not multiply by the distance. Now, shear force at F, that is F, we know that it is 0. But what is the expression? So what I have done is, I have taken this distance. Now we have to find this distance. From C, at what distance that shear force is 0 or that point F is there. That distance I have taken as x1. So now I am here. You write the shear force expression at F1 by seeing to the left side of the section. Because I have taken the distance from the left side. The left side of the section you see. So shear force, that is sign convention. At the last I have written, this is sign convention. Left side upward positive, downward negative. So 76.25 is positive and this 15 is negative, this UDL is negative. So this UDL you have to convert into concentrated load 30 into 1 plus x1. 30 into 1 plus x1 is the equivalent concentrated load, that is also negative. So you can see that 76.25 minus 15 minus 30 into 1 plus x1, this should be equal to 0 because we know the value of shear force at F as 0. Now if you solve this equation, you will get the value of x1 as 1.04 meters. So that means this F is at a distance of 1.04 meters from C to the right side. So that's what I have written here. The x1 is this value. Now once you know the point where the shear force is 0, now at the same point you can see that bending moment is maximum. Now at the same point F, you calculate bending moment. For calculating bending moment, this is the sign convention you have to use. Left side, upward forces give positive bending moment or sagging, it will be like this. Downward forces give negative bending moment, hogging, it will be like this. Now here, upward forces, if you see to the left side of F, if you start calculating the bending moment due to this 76.25 kN is 76.25 into 1 plus x1. Now you can substitute the value of x1 as 1.04, 1 plus x1 means 2.04. So it is upwards, therefore positive. Then this UDL is acting downwards, so bending moment is negative. So minus 30 into that 1 plus 1.04, the distance, that is the total UDL, and it acts at the midpoint. So you can see here 30 into 2.04 is the length of that UDL, and it acts at the midpoint means it is 1.0, the half of this. from the point F. So that is negative because it is acting downwards. Next, coming to the point load, this also we have to take. So 15 into 1.04. So that is also negative. Now if you simplify this, you get 77.53 kN meter. That is the maximum value of bending moment which occurs at F, where the shear force is 0. So here we have seen that it is 61.25. Here it is 60.75 kN meter. In between that it exists. So between C and D, somewhere between C and D, your F is there. So therefore, maximum value of bending moment is this much. Now he has asked one more thing. After getting the maximum value of bending moment, draw the bending moment diagram. Then only after drawing the bending moment diagram, then only you can locate the point of contraflexion where the bending moment is 0. Now here, once you get the values of bending moment, start plotting the values. So draw a horizontal line once again, where it represents the axis of the beam. Positive values you have to show above the line, negative values you have to show below the line. Now at A it is 0, bending moment is 0. Next point is C. At C it is 61.25 kN. Then at F it is 77.53, slightly above that we have to show. It need not to be scaled, but you have to write the values. Then at D it is 63.75, it decreases from F to D. Then at B it is negative 22.5, you have to show below the line. Then at E it is 0. So locate all these points and how to join them. So you know that the profile of bending moment diagram for UDL is parabola. You have to keep that in mind. Concentrated load is straight line. For UDL is parabola. So from A to D you have the parabola because UDL is there. So you have to join like this. So this is smooth parabola, smooth curve like this. So highest value you have to show at this point F. Then afterwards it is straight line. From B to B it is straight line, B to E it is straight line. So please note that from A to G, it is positive bending moment. From G to E, it is negative bending moment. That is, sagging effect will be there from A to G, and from G to E, you have the hogging effect. Now, at this point G, bending moment is 0. So where the bending moment diagram cuts the horizontal line on the axis of the beam line, so there you have the bending moment as 0. Now I have to locate this point. Bending moment is 0 we know, but at what point? At what distance? So now this point I have taken as G. Now let me take this distance as x2. Distance of G from B, I am going to take it as x2. Now I have to find the value of x2. So to find the value of x2, that point is called as point of contraflexion. G is the point of contraflexion and bending moment is 0. We have to write down the bending moment expression at G and equate it to 0. So for writing bending moment expression, we have to use this sign convention. So what I have done here is, I have taken right side of G. Right side of G, upward forces give positive bending moment, downward forces give negative bending moment. So here, from here, so this force is there, now G is here. So to the right side, 43.75 into x2. This distance is x2. That is positive because upward force. Then minus 15 into x2 plus 1.5. See here, I have written this. That will be equal to 0 because this value we know, bending moment at D is equal to 0. Now by solving this, you will get the value of x2 as 0.782 meters from B to the left side. To the left side of B, you have that value or that point G. So this is the point of contraflexion. This is the point of maximum bending moment. So in any problem, they may ask you to find the point of contraflexion, also point of maximum bending moment. So it is opposite. Of course, point of contraflexion means bending moment is 0. Maximum bending moment means shear force is 0. So like that we have to think and we have to do. So this is an important problem from the examination point of view. After getting this sagging and hogging effect, you can always, the meaning of that is, I told you, so by getting the BMD, so we can judge what portion of the beam sags and what portion of the beam hogs. So here you can see that from A to G you have a sagging effect. So if you want to draw the elastic curve, see it is like this, something like this. The beam deflects like this. Sagging effect will be there from here to here, whereas you can see the hogging effect from here to here. See, this is how the axis bends. In the case of overhanging beam, you can have the shape like this. So sagging effect means if it bends like this, hogging effect means it lifts, the axis is lifted, gets lifted like this. So this is called as the elastic curve or the deflected curve. This is called as elastic curve or deflected curve. So you should have an idea how the axis of the beam bends when it is subjected to external loads. So after getting the BMD, then we can decide from what point to what point sagging effect will be there, from what point to what point hogging effect will be there. Then only you can draw the elastic curve. Thank you very much.